Hello, everyone, and welcome back. And today we're going to be talking about the origins of modern astronomy. Just as a table of contents, we're going to be going over this week in astronomy and the history of astronomy. Right, so this week in astronomy, we're going to start off with the James Webb Space Telescope. And the James Webb Space Telescope recently took a really nice image of the pillars of creation. As always, these images are in infrared, and so they can see more young stars that would be forming in this large galaxy. And here are just a couple of photos. Next, it saw this fingerprint in space. That was pretty cool. Look at that. Those are actually the gravitational waves of the stars moving the dust that they emit around them into spherical patterns, which we see as waves. So that's pretty cool. All right, now for the big boy for the Hubble Space Telescope. Um, so I took a photo of this galactic triplet called ARP. As we can see, we have one galaxy over here, another galaxy over here, and one over there. Next is the NGC 1999 nebula. This one's pretty cool. Um, Next, we have these two stars. Pretty cool, pretty cool. Terra star cluster. Very nice. All right, so starting off with the history of astronomy. Let's start off by talking about early astronomy. Earth is one of the 9 planets and many smaller bodies that orbit the Sun. There are billions of galaxies in the universe, and the Sun is a much smaller part of just one galaxy. And a few hundred years ago, scientists thought the Earth was at the center of the universe. So ancient Greeks believed that astronomy is the science that studies the universe, and astronomy deals with the properties of objects in space and the laws under which the universe operates. So the golden age of early astronomy was centered in Greece and happened from around 600 BC to 150 AD. The early Greeks used philosophical arguments to explain natural events, but they relied mostly on observations. The Greeks used instruments such as the astrolabes to track the motions of the stars and the sun. The Greeks also developed the basics of geometry and trigonometry, which were incredibly helpful to make astronomical calculations back then. And using these branches of mathematics, they measured the sizes and distances of the sun and the moon. The Greeks made many astronomical discoveries. One of the most famous Greek philosophers, Aristotle, concluded that the Earth is round because it always casts a curved shadow when it passes between the sun and the moon. And Aristotle's belief that the Earth is round was largely abandoned in the Middle Ages, even though Aristotle's other theory about geocentrism was incredibly popular at the time. So the first successful attempt to establish the size of the Earth is credited to a Greek mathematician known as Eratosthenes, and he observed the angles of the noonday sun in two Egyptian cities that were roughly north and south of each other, which were Syene and Alexandria, and he used that to calculate basically how much distance was between them, and then extrapolated that to account for the entire circumference of the Earth. And his answer was actually 95% accurate of what we know of the Earth's size today. So by finding the angles, and he found that the angles differed by 7 degrees, or around 1/50th of a complete circle, he concluded that the circumference of the Earth must be 50 times the distance between these two cities. And so these cities were 500 stadia apart. A stadia is like 2 miles-ish. And he gave him a measurement of around 250,000 stadia, which is incredibly accurate. Many historians believe that the stadia was 157.6 meters, and this would make his calculation to come out around 39,400 kilometers, which is incredibly close to modern circumference measures of 40,075 kilometers. So probably the greatest of the early Greek astronomers was Hipparchus, and he was best known for his star catalog. And he determined the location of almost 850 stars, which he divided into 6 groups according to their brightness. He measured the length of the year to within minutes of the modern year and developed a method for predicting the times of lunar eclipses to within a few hours. And so at that time, a lot of Greeks believed in what is called the geocentric Earth theory, and they thought that the Earth was a sphere that stayed motionless at the center of the universe and everything else orbited around it. In the geocentric model, the Moon, Sun, and the known planets Mercury, Venus, Mars, and Jupiter orbit around the Earth. But they also thought that beyond the planets was a transparent, hollow sphere on which the stars traveled daily around the Earth, and this was called the celestial sphere. To the Greeks, all the heavenly bodies except 7 appear to remain in the same relative position to one another. These 7 wanderers included the Sun, the Moon, Mercury, Venus, Mars, Jupiter, and Saturn, and each was thought to have a completely circular orbit around the Earth. The Greeks were able to explain the apparent movements of all celestial bodies in space using this model. This model, however, was clearly not correct. The heliocentric model was developed by Aristarchus, and he was the first Greek to believe in a heliocentric model. And in the heliocentric model, Earth is just another planet that orbits around the Sun. Aristarchus used geometry to calculate the relative distances from Earth to the Sun and from Earth to the Moon, but he came up with measurements that were much too small, and that's one of the big reasons why no one believed him. However, he did learn that the Sun was many times more distant than the Moon and many times larger than Earth. Though there was evidence to support the heliocentric model, the Earth-centered view dominated Western society for nearly 2,000 years. Much of our knowledge of Greek astronomy comes from Claudius Ptolemy, and in a 13-volume work published in 141 AD, Ptolemy presented a model of the universe that was called the Ptolemaic system. It accounted for the movements of the planets as well as retrograde motion of the planets. Just like the Greeks, Ptolemy's model had the planets move in a circular orbit around a motionless Earth. However, the motion of the planets against the background of the stars seemed odd. Each planet, if watched night after night, moved slightly eastward among the stars. Periodically, each planet would also appear to stop and reverse direction for a time, and then resume in an eastward motion. This apparent westward drift is called retrograde motion, which I talked about. And this rather odd apparent motion results from the combination of the motion of the Earth and the planet's own motion around the Sun. However, Ptolemy's model accounted for something else. He said that each single planet has something called an epicycle, and these epicycles are basically planets moving in a circle around a center of orbit, and that's what he used to explain these retrogrades that we see today. And so the birth of modern astronomy, right? So the development of modern astronomy involved a break from previous philosophical and religious views, and scientists began to discover a universe governed by natural laws. 5 of these noted scientists are Nicholas Copernicus, Tycho Brahe, Johann Kepler, Galileo Galilei, and Sir Isaac Newton, many of whom I am sure you are very familiar with. So, Nicholas Copernicus, my man. For almost 13 centuries after the time of Ptolemy, very few astronomical advances were made in Europe. Obviously, these were known as the Middle Ages. And the first Greek astronomer to emerge after the Middle Ages was Nicholas Copernicus from Poland. And he became convinced that Earth is just a planet, just like the other 5 planets that were known. And the daily motions of the heaven and the celestial sphere, he reasoned, could be better explained by a rotating Earth. He concluded that the Earth is just a planet, and he changed the model of the solar system to having the Sun at the center, and the planets Mercury, Venus, Earth, Mars, and Jupiter, and Saturn orbiting around it. So this was a major break from the ancient idea that a motionless Earth lies at the center. And Copernicus used concentric circles, which were considered to be the perfect geometric shape, to represent the orbits of these planets. Although these circular orbits were close to reality, they didn't quite match what people saw. And that's where Tycho Brahe comes in. Tycho Brahe was born of Danish nobility 3 years after the death of Nicholas Copernicus, and he became incredibly interested while watching a solar eclipse that had been predicted by astronomers. And the telescope had not actually been invented at this time, so all of Tycho Brahe's incredibly precise measurements were all made from his eye. And so at his observatory, Tycho Brahe designed and built instruments called pointers, which he used for 20 years to measure the locations of the heavenly bodies. And according to Brahe's observations, especially of Mars, they were more precise than any that had been made previously. In the last year of his life, Brahe found an able assistant named Johann Kepler. And Kepler kept most of Brahe's information and put them to exceptional use. So Johann Kepler, just a little bit about him. Copernicus ushered out the old astronomy, and Johann Kepler ushered in the new. Kepler had a good mathematical mind and a strong faith in the accuracy of Brahe's work. Kepler discovered 3 laws of planetary motion. The first 2 laws resulted from his inability to fit Brahe's observations of Mars to a circular orbit. He discovered that the orbit of Mars around the Sun is not a perfect circle. Instead, it's an oval-shaped path called an ellipse. Almost about the same time, he realized that the speed of Mars in its orbit changes in a predictable way. As Mars is orbiting closer to the Sun, it speeds up, and as it moves away, it slows down. After decades of work, Kepler summarized 3 laws of planetary motion. Number 1, the path of each planet around the Sun is an ellipse. Number 2, each planet revolves so that an imaginary line connecting to the Sun sweeps over equal areas in equal intervals, which basically means that a planet moves faster when it's closer to the Sun. And 3, the length of time it takes a planet to orbit the Sun and its distance are proportional. In its simplest form, the orbital period of revolution is measured in Earth years. And a planet's distance to the sun is expressed in something called an astronomical unit, which is the average distance between the Earth and the sun. And so using these units, Kepler's third law states that the planet's orbital period is equal to its mean solar distance cubed. Therefore, the solar distances of the planets can be calculated when their periods of revolution are known. Here comes my man Galileo Galilei. He was the greatest Italian scientist of the Renaissance period, and his most important contributions were his descriptions of the behavior of moving objects. All astronomical discoveries before his time were made without the aid of a telescope. And in 1609, Galileo heard that a Dutch lensmaker had devised a system of lenses that magnified objects. Apparently, without ever seeing a telescope, Galileo constructed his own. It magnified distant objects to 3 times the size seen by the unaided eye. And so using this telescope, Galileo was able to make a lot of very important observations for modern astronomy. So his first observation was that there are 4 moons or satellites of Jupiter. And this proved wrong with the old idea that the Earth was the only center of motion in the universe. And it proved it wrong because it was proven that Jupiter also has other concentric circles that are orbiting around it. Here, plainly visibly, was another center of motion, which was Jupiter. People who opposed the sun-centered system said that the moon would be left behind if Earth really revolved around the sun. Galileo's discovery incredibly disproved this argument. So the discovery that planets are circular disks and not just points of light, as previously thought. This showed that the planets must be Earth-like as well. And third, he discovered that Venus has phases just like the moon, and so Venus orbits its own source of light, the sun. Galileo saw that Venus appears smallest when it's in full phase and therefore is farthest from the Earth. He also discovered that the moon's surface was not incredibly smooth. He saw mountains, craters, and plains, which can all be seen today with a normal telescope if you have one, so I highly encourage you to go out there and check it for your own. He thought that the plains must be bodies of water, which was wrong, but not as wrong as some of the other things that earlier astronomers had said. And this idea was also believed by others, as we can tell from the names given these features. And so his fifth observation was that the discovery of the sun had sunspots or dark regions. Galileo tracked these movements of the spots and estimated that the rotational period of the sun is just under a month. And then comes my man Sir Isaac Newton, and he made the 3 most important laws in modern physics. At the age of 23, Newton described a force that extends from Earth into space and holds the moon in orbit around Earth. He called this thing gravity. So according to Newton, every body in the universe attracts every other body with a force that is directly proportional to their masses and inversely proportional to the square of the distance between them. And so this law of universal gravitation also states that the greater the mass of the object, the greater its gravitational force. And so the mass of the object is the measure of the total amount of matter that it contains. Often we confuse the concept of mass with weight. Weight is just how much gravity an object experiences, whereas mass is the amount of matter in an object. Newton proved that the force of gravity, combined with the tendency of a planet to move, of a planet to remain in straight line motion, results in the elliptical orbits that Kepler had discovered. He concluded that it is the combination of Earth's forward motion and its falling motion that defines its orbit. Newton used the law of universal gravitation to redefine Kepler's third law, which states that the relationship between the orbital periods of the planets and their solar distances cubed. When restated, Kepler's third law takes into account the masses of the bodies involved and provides a method for determining the mass of a body when the orbit of one of its satellites is known.